We've discussed that high sensitivity was a must for a sampler, which includes a low DC offset, but we never talk about the sampler's intrinsic noise. When should we start to look at the sampler noise carefully? Why should we even need a dedicated noise analysis for a sampler, such as a strong-arm latch comparator? Bingo! The first question of when we should start to look at the sampler noise is when we apply the sampler at a high speed. From a signal perspective, the channel loss or the multi-level, for example, painful signaling, reduce signal power more at a high speed. If the noise stays the same at the RX input or the channel output, the SNR will be smaller due to the smaller signal. Unfortunately, by making the sampler clock-to-Q delay shorter or making the sampler's regeneration time speed faster, the intrinsic capacitance at the sampler must be smaller to reduce the charge and discharge time constant. On the other hand, the intuitive way of a random noise would be KT on C noise, which implies a small C would lead to a bigger thermal noise. Therefore, the sampler's input sensitivity would degrade due to a less SNR from a smaller signal power but a higher intrinsic noise. Therefore, we probably don't care about the sampler noise a lot while the data rate was 5 gigabit per second, but we need to be very careful when we start working at 32 gigabit per second PCIe Gen 5 or beyond 112 gigabit per second painful SerDes. Do you have any idea of the noise analysis for sampler? Let's review or recall the noise analysis we learned from the Microelectronics 101. First, we know the input reference noise is a fair quantity to compare different noise circuitry regardless of different amplification gains. Then, second, we can simply knock out the input source by either shorting the input voltage source or opening the input current source. Third, measure the total output noise from all the noise sources. Lastly, we can get the input reference noise by the total output noise voltage divided by the gain. If we are doing an AC noise simulation in SPICE, those procedures will be exactly what the simulator calculated the noise of your circuit. Can we apply the same AC noise for the strong-arm latch sampler? Think about the amplifier noise image for 5 seconds. Bingo! The AC noise we applied was based on linear amplifier where the small signal model can apply well. In addition, the gain of the amplifier is assumed to be the same all the time, which means it's a time invariant system. Therefore, the AC noise was straightforward to be analyzed and calculated simply divided by the gain. Is that the same case for a sampler? Of course not. First, the sampler is a nonlinear amplifier because of the regeneration latches. Secondly, the sampler is a time-variant system. Think of all the operations more in time, the sampling, the regeneration, and reset phases. So, first, how do we calculate the output noise of a sampler if it's not a linear amplifier with a small signal modeling? Second, how do we get a sampler gain if it's a time-variant system? Think about each phase operation images for 5 seconds. Right, let's start with the reset phase. As you can see, the reset phase will shorten the output to VDD and PQ to the same level. Therefore, not only the output differential signal, but also the output differential noise will be little. In addition, during the reset phase, no one will care about the noise here, since no decision or error could be made during this phase. This will simplify our noise analysis, even though it's a time varying system. What's the next phase? Is that the dominant phase of our noise analysis? Yes, sampling or amplification phase. In the sampling phase, the input differential pair amplifies the input tiny differential signal. Therefore, the input referred noise is dominated by the input pair M1, M2 from the current integration activity, and the initial state at P, Q from the transistor M9. Therefore, the intuitive noise source was defined by Kt on C noise at node P and Q. If the capacitance is bigger, the less disturbance would lead to a less noise. Similarly, for the input differential pair, a higher threshold voltage of the input pair M1 and M2, the input will have more immunity and less dependence in noise. Another observation is the input common mode voltage must be small enough to keep less disturbance and noise low enough. Unfortunately, all those factors of lowering the noise, like increasing the capacitance, increasing threshold voltage, and reducing the overdrive, would reduce the speed. Therefore, optimized transistor sizing and biasing would be a must with the aid of a simulation, which we will describe in detail later. What's the next phase? Great. Then let's go through the regeneration phase 1 with the M3 and 4 to drop the Vout voltage further until the M5 and 6 are turned on. In this phase, the noise has much less contribution to the overall decision compared to the input differential pair, but it still has some noise contribution. To reduce the noise from M3-4, we should make it bigger, but that may reduce the speed due to the self-loading capacitance. What's the last phase? Correct. The final regeneration phase will finish the whole positive feedback around this transistor and eventually bring one output back to VDD while allowing the other fall to 0. Intuitively, the output have reached rail-to-rail level with a much higher voltage gain in the end. Therefore, the input referred noise is much less from the M3, 4, 5, and 6 at this phase. Here are the summarized images of why we need a dedicated noise analysis for a strong arm latch comparator. First, the channel loss or multi-level, for example, painful signaling, reduce signal power more at a higher speed. In addition, to speed up the sampler's regeneration time, the intrinsic capacitance at the sampler must be smaller to increase the Kc on C noise intuitively. Therefore, the sampler input sensitivity would degrade due to the less SNR from a smaller signal power and a higher intrinsic noise. Therefore, we did not watch out for the sampler while the data rate was only 5 gigabit per second. But we need to be very careful when we start working at 32 gigabit per second and beyond 112 gigabit per second painful series. Initially, we know the AC noise analysis from a small signal model we learned from Microelectronics 101 will apply to any LTI system, but not a sampler, which is a nonlinear and time-varying system. Fortunately, we could look at the sampler noise at each operation phase. First, in the reset state, the noise is little, and we don't care about the noise as well, since it's not a decision phase. But second, in the sampling phase, we do care about the noise, since it's very sensitive at the phase to making a wrong decision due to the noise. Without looking at any equations, we know the bigger capacitance at P, Q would help reduce noise, since the charge would have less disturbance at the differential pair's output. On the other hand, lower the threshold voltage or the overdrive of the input differential pair would lead to a low noise as well. However, the noise reduction at the sampler's design will lead to a lower speed as well. Therefore, we must optimize the sizing through a spice simulation later to get the noise analysis precisely. Lastly, the regeneration phase would have little noise impact or contribution of the input reference noise of the sampler, and we just need to make sure not to oversize those latches to reach self-loading capacitance and degrade the speed. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.